So to finish up section 0.2, we're going to talk about functions. Surely by now you've seen functions in an algebra class or pre-calc or calculus. But more generally, we want to make sure that we have an idea of what a function is, sort of in a more general way. So a function is just a rule that assigns or maps the elements of one set to the elements of another set. Okay, so if f assigns every element of A to some element of B, we would write f is a function from A to B. So f colon A arrow B is how we say f is a function with a domain of A and a codomain of B. So the elements in the first set, the inputs are the domain of the function, and the set of potential or allowable outputs we call the codomain, that's B. These two sets are usually given to you. Oftentimes in calculus you can sort of just determine it based on context. But in this class, usually there'll be something that's sort of given or that's understood from the problem. Now, the actual outputs of the function is what we call the range of the function. So the set B is the codomain. Those are the allowable outputs, but the actual outputs are the range. So what this means is that the range is always going to be a subset of the codomain. Possibly equal, but certainly not any bigger. And finally, each input x in the domain has to have exactly one output y in the codomain. And if x is getting mapped to y by this function, we would use a notation that f of x is equal to y. This is just saying that the input x is getting mapped to the output of y. All right, there's lots of different ways that you can describe a function. Sometimes we use an equation, like in calculus we usually do an equation. We can also use a diagram. And so in this first example, let's say the function f has a domain of natural numbers and a codomain of integers. And it's defined by the equation f of x is equal to negative 2x. We can sort of draw a picture as follows. The input of 1 is going to give you an output of negative 2. That's because f of 1 is going to be negative 2 times 1, which is negative 2. Similarly, f of 2 is going to be negative 2 times 2, which is negative 4. F of 3 would be negative 6, etc. Okay, the domain and the codomain were given to you, right? The domain was the natural numbers and the codomain was the integers, but the range is a set of actual outputs, and we can sort of argue that the actual outputs of this function are always going to be even numbers, right? Because it's negative 2 times some positive number. And they're going to be negative. And so the actual outputs, or the range of this function, is going to be the set negative 2, negative 4, negative 6, negative 8, etc. Okay, so notice that the range is a subset of the codomain, but they're not equal in this case, right? Some elements of the codomain are not actual outputs of this function. Nothing's going to map to 5 or negative 5. All right, a couple more examples. Let's define a function g with a domain of 1, 2, 3 and a codomain of ABC by g of 1 is equal to a, g of 2 is equal to a, and g of 3 is equal to b. I'm going to just sort of demonstrate this with a dot diagram here where I put my domain on top, 1, 2, and 3, those are my inputs, and my codomain on the bottom, a, b, and c. So this is saying that 1's going to map to a, 2's going to map to a, and 3 is going to map to b. This is a function. This is a perfectly good function because every element of the domain gets assigned to something in the codomain. Notice that nothing gets mapped to C. That's okay, right? Not every element of the codomain has to be in the range, has to be an output of the function. And it's allowed for two different elements of the domain to be mapped to the same element of the codomain. That's fine. All right? But if we look at example 3 here, consider a rule H defined by H of 1 maps to A, H of 1 maps to B, H of 2 maps to C, and H of 3 maps to B. This diagram is going to look like 1, 2, 3, A, B, C. This is saying that 1's going to both A and B. 2 is going to map to C, and 3 is going to map to B. This is not a function. And the problem here is that the input of 1 has two different outputs. This is not allowed, right? Any one single input cannot give you two different outputs. This is not well defined because f of 1, or the input 1, oh, I should call it h of 1, not f of 1. Input 1 has two outputs. That's not allowed in a function. Okay, so two different inputs can give you the same output, but the reverse of that is not true. One single input can't give you two different outputs. With that in mind, we can look at this exercise here. It says if x is a set consisting of the numbers 1, 2, 3, 4, y is a set consisting of a, b, c, d, which of the following represents a function? All right, this first one, does every single input have an output? Yes, and that's it, right? As long as every input has an output in the codomain, this is a function. Similarly, for the second example, every input has an output. That's in the set y, so yes, this is a function as well. But for this last one, there's actually two reasons why this is not a function. First of all, the input 2 gives you two different outputs, which is bad. Right? H of 2 has two different outputs, so it's not well defined. H is not well defined. But there's actually another problem with this as well, which is that my domain consists of the numbers 1, 2, 3, and 4. And the number 1 hasn't been mapped to anything. H of 1 is undefined. That's a problem because 1 is in the domain, which means 1 should be mapped somewhere, right? These have to be good directions. You have to be telling everyone in the domain exactly where to go. 1 doesn't know where to go, and 2 doesn't know where to go either because 2 is being mapped to two different outputs. So this last example is not a function. Now, if we wanted to try and specify that we want a function where this scenario doesn't happen, let's try and highlight it up above. Right, if we wanted to try and specify that I don't want two different inputs to give me the same output, you can do that, right? Some functions won't have that property, but some functions will have the property that two different inputs are guaranteed to give you two different outputs. And so we describe that by saying a function is one-to-one. Sometimes, I should add here, we also call it injective. So a function f from a to b is one-to-one or injective if no two elements of a have the same output in b. All right, so for example, this is one-to-one because every element of the domain gets its own unique output. But the second example is not one-to-one because we have two elements of the domain that have the same output. So just to be clear, another way of describing this property of being one-to-one is by saying that if you take two distinct elements of the domain, A, you're guaranteed to get two distinct elements in the codomain. In other words, we could say that, let me do this down below, f is injective if and only if for every pair of elements, let's say x1 and x2 in the domain, if x1 and x2 are two different elements, then f of x1 and f of x2 are two different elements. So if you start with two different elements of the domain, you're going to end up with two different outputs. That's what it means to be one-to-one. Okay. Now we also have another second property which is sometimes important in functions, which is the onto property. This says that a function from a to b is onto if for every element y in the codomain, there is an element x in the domain that maps to it. Right? In other words, the range is equal to the codomain. Everything in the bottom row gets used as an actual output. So this is onto because the range, the actual outputs, is equal to the codomain, but this is not onto because nothing maps to this center element. And again, I guess I should add, another word for onto would be surjective. So if we wanted to describe this surjective property, we would say that f is surjective if and only if we want to say that every element of the codomain, every element of B, is an actual output of the function. So we would say for all y in the codomain, you can find an element x in the domain such that f of x is equal to y. Or you can find something in the domain that maps to that y. Okay. As one last example, if we look at the function from n to n, from the natural numbers to the naturals, defined by f of n is equal to n plus 1, is this a bijection? Whoops, let me go back. If a function is both 1 to 1 and onto, we say it's a bijection. So we want to find out if this is a bijection. So we want to know, is it 1 to 1 and onto? So to check that it's 1 to 1, we need to check that for every x1 and x2 in the domain. That's the set of natural numbers. If x1 is not equal to x2, does that imply that f of x1 is not equal to f of x2? That's how we would prove that this is a 1-to-1 function. And we can see from the picture this seems to be the case. But to prove it rigorously, we're going to let x1 and x2 be natural numbers that satisfy the hypothesis, right? That satisfy x1 is not equal to x2. So how do we know that two different natural numbers are going to have two different outputs? Well, if you take two different natural numbers and you add 1 to each of those natural numbers, you're going to get two different natural numbers, right? Since x1 is not equal to x2, it follows that x1 plus 1 is not equal to x2 plus 1, which means f of x1 is not equal to f of x2. In other words, if the inputs are different, then the outputs are different. So this function is 1-to-1. Okay. Is it onto, right? To be a bijection, you have to be 1-to-1 and onto. So to check that it's onto, we need to show that for every y in the codomain, that in this case is also the natural numbers, there exists an x in the domain, that's the natural numbers, such that f of x is equal to y. Looking at the diagram, it's easy to see that this doesn't seem to be onto. We do have one leftover element in the bottom row in the codomain that's not in the range, that's not an output of the function. In particular, nothing's mapping to the number 1 here. This is not onto. If we let y be equal to 1, then no element x is going to satisfy that f of x is equal to 1, and that's because f of x is defined to be x plus 1, and so the only potential x value would be x equals 0 if you want to have an output of 1. But x equals 0 is not in the domain. It's not a natural number. Right, so no natural number is going to map to 1. Therefore, the range is not equal to the codomain, so this is not onto. And since it's not both 1-to-1 and onto, this is not a bijection.